and giving me the opportunity to speak about a subject I have worked for the last, say, few years on it. So the title in the abstract is a little bit different, but this is more precise. So Besov-type spaces are just smoothness spaces related to Morrey spaces as a basic space. So you replace LP by Morrey and look for the outcome. All what I'm going to tell here is joint work with Dachun and Yuan, which both are present. At least Wen is here, but Dachun may return in a minute. So a few words to the Haar system. Of course, I believe that all are familiar with the Haar system. So the generator of the Haar system is a function, a step function, which has value 1 on the interval 0, 1/2, and on 1/2, 1 value -1. And let me use the terminology from the wavelet theory. So the function h tilde here, this is just this function, the Haar wavelet. And the Haar wavelet is a wavelet associated to the scaling function given by the characteristic function of the interval 0, 1, which is denoted by this chi with tilde. And if you introduce these tensor products related to a vector epsilon consisting of being a vector of zeros and ones, then you get the generator of the d-dimensional wavelet system related to the Haar system. So if you choose epsilon always 0, then the function, the outcome is a characteristic function of the unit cube in d dimensions, and the other elements here are the 2 to the d-1 generators of the wavelet Haar system. So I use standard notations from wavelet theory. So we have shifts here and scaling here, properly normalized in L2, and then the corresponding system I call a Haar wavelet system in RD. I try to avoid the name basis because in my talk the basis property will not play a role in some sense. I'm interested in a little bit weaker property. You will see at the end why. So this system is of course an orthonormal basis in L2. It's an unconditional basis in LP, and it's also an unconditional basis in some Besov spaces. So let me recall this a little bit. So Besov spaces we have seen yesterday in the talk of Yuri Malichin. And here I pick up the same idea to start with differences. Of course, you can introduce Besov spaces in different ways: Fourier analysis, atoms, molecules, wavelets, etc. There are many of those. So this abbreviation sigma p will play a role during my talk. If you deal with spaces with p less than 1, then the theory is a little bit more tricky compared to p bigger than 1, because then these are distribution spaces, and it may happen that you have singular distributions in those spaces, and then characterization by differences would not make sense. So many times I need an abbreviation, I need this condition that the smoothness S is strictly larger than this quantity, because it guarantees that we are dealing with regular distributions. So the most transparent way to characterize Besov spaces under this condition here is to use differences. Then you compare a first order difference, say the LP integral with respect to this difference, with the power of h to the minus s, and then you integrate. One example, this is easy to calculate, and my PhD students, at least most of them, at the beginning when they were forced to deal with Besov spaces, they had to do this little calculation by themselves. You take the characteristic function and try to figure out to which spaces these functions belong to, and then you will see it belongs to the Besov space with smoothness S equals 1 over P, integrability P, and fine index Q equal infinity, and this is true for all P. And then when you try to improve the result, that means you look for spaces with Q less than infinity, they are smaller, there is a monotonicity with respect to Q, then it's easily shown this will not happen. So this is a limiting case. In my talk also Besov spaces with negative smoothness show up. They also can be introduced in different ways. Let me recall that one can do this also by duality, accepting some restrictions, additional restrictions on that way. Then we have the nice formula. If you look for the dual of the Besov space, then you have just to change the sign of S, and instead of P you have to take P prime, and instead of Q you have to take Q prime. But then you are always confronted with some restrictions, which in general you don't need. So Haar wavelet and Besov spaces has been a popular topic over the years. There are several contributions, and this list is of course not complete. Probably the story began in 1973 with the first contribution by Triebel. Most important today for me will be the paper from 1978. 2010 and 2013 refers to the first one to a book of Triebel on Morrey spaces, and 2013 is a characterization of some Morrey type spaces by the Haar system. So of course I have to mention the Polish school here. I have mentioned Ciesielski and Ropela. At least in the paper of Ropela there are Besov spaces, as far as I remember, on the interval. So there's a close relationship on spaces on the interval and on RD. I will concentrate for simplicity on RD. Then I have to mention Peter Oswald. He started to investigate limiting cases. You will see in a minute which one. And he continued his investigation of the limiting cases last year. And I would like to mention a series of papers by my chairman, together with Andreas Seeger and Tino Ulrich. There are at least 4 papers devoted to this topic, not only in Besov spaces. So the first 3 of this series are devoted to the study of the little bit more complicated Lysorkin-Triebel spaces in this context. And as I said before, I'm not really interested in the basis property. I'm interested in the following question: under which conditions we can characterize Besov spaces in terms of the Fourier-Haar coefficients. So we look for a counterpart of the L2 result, that you can characterize the function space L2 by the sequence space of L2. But of course you have to expect that the sequence spaces will look a little bit more complicated. So therefore I need a little bit more of notation. First of all, I would like to incorporate the scaling function and the shifts of the scaling function in my notation concerning the generators of the Haar system. So I introduce this notation. I refers to the number of the generator, -1 is a new frequency level, and M is still the shift. And then we have to deal with the following sequence spaces. So first of all, you see here an LP structure. Here's a P, here's a P, and outside we have an LQ structure, and in the middle we have a weight depending on S, the smoothness, and depending on the distance of 1/2 to 1 over P. So a short test shows you if P is equal to 2 and S is equal to 0, and Q and P are equal to 2, then you are back in L2. So this is a generalization of L2 in some sense. And then the result of Triebel from 1978 looks like follows. So all P and Q are admissible. In particular, also infinity is admissible. So if either P is infinity or Q is infinity, the Besov spaces, the associated Besov spaces, are non-separable. So there is no basis at all. But we have still a characterization by the Fourier Haar coefficient, as it is written here. So we have the following restrictions, which will be important for the rest of my talk. So there's a lower bound, maximum 1 over P minus 1 D over P minus D. So immediately you become aware if P is larger than 1, then this is a real bound, and if P, and this is negative. And if P is less than 1, then this is a real bound and this is positive. So there's a change in some sense. And there is a limit from above, minimum 1 and 1 over P. And then the following is true. A tempered distribution belongs to the Besov space if and only if it can be represented in S prime, so in a very weak form, by this Fourier Haar series. At the end, it turns out, when your function belongs to the Besov space, then this conversion is not only in S prime, the conversion takes place in all these spaces Bs minus epsilon PQ. So if you lower the condition on the smoothness a little bit, then you have always convergence in norm. And we have to take the sequence of the Fourier Haar coefficient in this sequence space BSPQ. So there is a characterization of these spaces in terms of the Fourier Haar coefficients. And one knows even more, the mapping which associates to F the sequence of the Fourier Haar coefficients is an isomorphic map of the Besov space onto this sequence space. This means we can even work with this quantity as an equivalent norm. And this is quite helpful for several questions. You need not to deal with the function spaces itself. You simply can deal with the sequence spaces, which are, of course, easier to handle than the function space. So what about the restrictions? Let me explain these restrictions at least a little bit. So we are interested in the Fourier Haar series of the function. And if we require that the conversion takes place with respect to spaces with smoothness S minus epsilon for arbitrary epsilon, and if we take into account that we know the regularity of these functions in a Besov space, and it's easily shown that these functions have the same regularity as the generator, the scaling function itself, then it's easily shown that we need to have that the upper bound for S is 1 over P, because 1 over P was the smoothness of this function, the optimal smoothness. And then 2018 in the paper by Oswald, probably it's also somewhere hidden in the recent manuscript of these three authors, one can find the following transparent argument. If you consider S equals 1 and P less than 1, then the Fourier Haar series of this simple function here does not converge to F in the norm of this space. That means this is also a situation you have to avoid. And this leads together to the upper bound that S has to be less than or equal to 1 or 1 over P. So I will not take care of limiting cases. For me, it's enough to know what are, say, in principle, the restrictions. So this is an explanation for the upper bound of S. There are some more easy necessary conditions. So when we want to have convergence of the Fourier Haar series, of course we need to have that these mappings here are meaningful. That means that these mappings are linear and continuous functionals on the Besov space. And then there's a very simple argument. If you know that your Besov space is continuously embedded into L1, then you have this simple estimate, and that shows you that this is a well-defined linear functional. So when you look for this problem in distribution spaces, of course you may start to test with, say, a concrete distribution. The most simple example is a direct delta distribution. So can we give this simple a real meaning? So then it's more or less obvious. If you start with a C0 infinity function, integral is 1, then we know that this limit exists, and this is the value of f at 0. And that means, rephrased in the terminology of weak convergence in S prime, that these functions form a convergent sequence with limit delta. But then you may look for the following two special cases. If the support of phi is concentrated in this part of Rn, then we get that the limit is 1 if we take the scalar product of these functions with a characteristic function of the unit cube. If we shift the support to this part of Rd, then the outcome here is 0. So you cannot give a meaning to the brackets delta with characteristic function, and that means you cannot extend this mapping from BSPQ intersected with L1 to BSPQ as a linear and continuous function whenever delta belongs to this space. It's an easy exercise to calculate the smoothness of delta in Besov spaces. Therefore, it's most helpful to use a Fourier analytic approach, and then you can calculate the best what you can get is b d over p minus dp infinity. And what concerns the embedding in L1, it's also well known that if you change this fine index here to 1, then you have the embedding. So both results are sharp, but we are not far away from, they are not far away from each other. So we have almost done. So it needs a little bit more sophisticated test functions to show that the following characterization takes place. If p is less than 1, then the mapping which sends f to this brackets has an extension from the intersection of BSPQ with L1 as a linear and continuous functional on BSPQ if and only if these conditions here are satisfied, and that are exactly the conditions characterizing the embedding of BSPQ into L1. So there is no extension in cases where we have singular distributions, but this is only true for p less than 1. If p is bigger than 1 or equal to 1, the outcome is different. Then the limit for the extension to be linear and continuous on Besov spaces is given by this case. S is equal 1 over p minus 1. So, and of course, if S is 1 over p minus 1, if p is strictly larger than 1, this is less than 0. And the barrier for singular distributions they cannot overcome is exactly sigma p. So this is S equals 0 on 0, 1. Here I draw 1 over p against S. And this is a line with slope d, d over p minus d. So here we have singular distributions, and here we have regular distributions only. So for p strictly larger than 1, there are possibilities that you can also have, here singular distributions. So as I said before, these questions have been investigated by Peter Oswald last year. We did it parallel, but in a much more general context, as we will see in a minute. We have different techniques. Peter is working with differences to say and duality. We are working with sufficiently smooth double-G wavelets in the background. And much more on necessary conditions, in particular about associated projection operators, you can find in this very recent preprint. Summary. So if you allow values of P and Q in this maximal area, then you have to accept for a characterization as shown before that are the limitations. And it may happen that's wrong for equal sign here. This is not clear to me in some limiting cases, but in almost all cases it will be not true in the limiting cases. Besov-type spaces. What are Besov-type spaces? So it's not so important to understand the concrete definition, it's more important to understand the philosophy. So if we consider the most simple case, so S is less than 1, but we are in the region of regular distributions, then a function f belongs to a function f belonging to LP belongs to this Besov space with p equal q, if and only if this quantity here is finite. So this is almost the same as I have shown you on the second slide. There's only a little transformation of coordinates done. Then you get it in such a symmetric form. This form is called Gallardo norm by people in the PDE world. And this goes back to the year 1956 when Gallardo started to work with. And probably a few of you know that Besov wrote his PhD on Besov spaces in 1959, 1960. So a special case was already known. There was one more special case known by Nikolsky, of course, that was a case Q equals infinity. So Nikolsky was the first. So what we are changing now, we are changing the area of integration. Instead of controlling this quantity on RD times RD, we replace RD by cubes. So look here. So Q stands for an arbitrary dyadic cube. We could take arbitrary cubes, but then we have to require in addition that the sides are parallel to the axis, which is in case of a dyadic cube part of the definition. So we take the same quantity localized with respect to a cube, and then we compare the outcome with the volume of the cube to some power. So this is a little bit different type of regularity. You want to understand or you want to express the regularity of a function by controlling this quantity on cubes. So this is the main philosophy which is related to Morrey type spaces in general. So, and we also have to replace the LP term. Here it's enough to look for dyadic cubes, for large dyadic cubes, but I could replace here this restriction also by all dyadic cubes. So this is the main philosophy. Here is a more serious definition. This is in terms of the Fourier analytic description of those spaces. Probably you know. So if you know, then let me show you what are the differences. So we start with a smooth dyadic decomposition of unity, which is used in the Fourier image. So this f denotes the Fourier transform. We take the Fourier transform of f, multiply this with this weight function, and then we take inverse Fourier transform. This is measured in LP, but the integration is restricted to Q. Then the next place where is a little modification, so summation starts depending on the size of the cube. So if you have a dyadic cube with side length L of Q, then we introduce this quantity, we take the logarithm of the side length and then a minus, which means this is a real restriction for small cubes. For big cubes here is just 0. And there is a third change compared to the classic definition of Besov spaces in Fourier analytic terms. This is given by this weight depending on the volume. So these spaces have been introduced in 2002 by a guy from Morocco with name Al-Baraka, but there are two French mathematicians in the background. They have been advisors, Jaffra and Bordeaux. These are well known. So, and at that time it was just a test whether a part of the theory works in such a connection. Then 2008, Dachun, Yuan and Yuan have picked up this topic and have started a more serious investigation of these spaces. Let me give you a warning. There are several types of smoothness spaces related to Morrey spaces. So here I have written 3 more versions. So these spaces with the N, they are called Nikol skij-Besov Morrey spaces. And you will get these spaces if you shift the supremum from here to here. So that makes a difference. So if Q is not equal to infinity, these spaces are really different, and nobody knows which are the good spaces. So at the moment I believe in these spaces here, but it may happen that I change my mind in 10 years. So, and these two that are related F spaces. So of course there's a question why. For me it's enough to say I'm interested in, but probably you want to know a few more answers, and here I use a simple way because lack of time. So 2 Japanese mathematicians, Kusono and Yamasaki, they, at least Kusono is working on Navier-Stokes equations in the long time. They introduced these Besov-Morrey spaces and used them in connection with Navier-Stokes equations. So the people in Navier-Stokes equations, they are looking for new appropriate notions of regularity, and that was just an attempt. There's a recent book about Navier-Stokes equations. So the Navier-Stokes problem in the 21st century by Pierre-Gilles-Lemerrier-Rieusseux. And in this book you will find these Besov-type spaces as one element of a list of spaces which are in some sense suitable for Navier-Stokes equations. So I do not claim that these spaces are essential for solving this problem. I just claim they might be helpful, and if you want to know details, please have a look in this interesting book. Properties. What are the properties? I have forgotten to say, just one moment. So here's a parameter tau. This is a new parameter, so showing up at this place. I will call this parameter Morrey parameter. So if you choose a Morrey parameter 0, then you are back in the classical case. But this is an exceptional case, as I will explain in a minute. Another interesting feature is if you choose the Morrey parameter equal 1 over p and p equal to q here, then we end up with the Sorkin-Triebel spaces with p equals infinity. So this is a result by Fraser and Yobert in their fundamental paper from 1990 without knowing that those spaces exist. But it's a nice fact that these spaces become a standard member in some sense of this scale. What is most important for my talk is if t is strictly larger than 0, then these spaces are non-separable. So there is it's meaningless to ask for basis. So the influence of the Morrey parameter can be shown in particular by looking for embeddings. If you look for an embedding into the space of continuous uniformly continuous and bounded functions, then the if and only if condition looks like this. So the parameter tau makes this condition weaker. So you may understand the tau as an additional smoothness parameter. For this reason, it's as a third index written next to S. But it could be understood in different connections as also a parameter influencing integrability. So what is the outcome? So this is the main result of my talk, which I would like to present here. Under these conditions, We have a similar result for these Besov-type spaces as in case of the Morrey spaces. A function, a distribution belongs to this Besov-type spaces if it has a representation in S prime given by its Fourier Haar series, and we have a condition in terms of a sequence space, I will explain in a minute, where only the Fourier Haar coefficients are used. And the mapping is again an isomorphism of this function space to the sequence space. If you look for the condition with respect to S, so the lower condition is as before, no influence of the Morrey parameter, but the upper restriction shows an influence of the Morrey parameter. So let me explain this a little bit. So what concerns the sequence spaces? Here I recalled the notion from the Besov space. So this main structure of the new sequence space we have to introduce is quite similar. But there are again 3 points which have changed. First of all, here is a localization of the summation. So we start with a dyadic cube and we ask for those dyadic cubes. QJM denotes the dyadic cube with side length 2 to the minus j and left lower corner in the point 2 to the minus j times m. So we ask only for summation with respect to those m where this dyadic cube is a subset of the dyadic cube from this point. Then we have again a restriction of the summation depending on the size of p, on the side length of p. And we compare this with the volume of p to some power. So these are the 3 places where changes happen. And then we start to understand whether the conditions I have shown you are meaningful or whether it's just an outcome of the technique we have used. And then it turns out the smoothness of the characteristic function in terms of these spaces. This depends to a certain extent on the Morrey parameter. So the limiting case is again S equals 1 over p, but there is a second condition where tau is showing up. If tau is getting larger, the smoothness requirements here in this space are getting more restrictive, and then we get an additional restriction for S. So the limiting case where this happens, if you compare these 2 restrictions, is given by tau equals d minus 1 divided by d over p. So the additional restriction you have seen here, this comes from the smoothness of the characteristic function. So that has a simple explanation. Next, we wanted to understand what about this mapping, under which conditions we end up with a linear and continuous functional. And then we have been able to characterize this in case p is larger than or equal to 1. But the picture becomes a little bit more complicated, probably I should say more colorful, sounds better. So we have to distinguish between small tau and large tau. So again, the limiting case is this quantity which has been shown up before, and then we have S equals 1 over p minus 1, S in case of tau equal to 0 and q less than or equal to 1, or S strictly larger than this quantity, and then all q are admissible. And there is a new case when tau is large, then we get a weaker restriction. This quantity here is smaller than 1 over p minus 1. So this is not easy to understand, but let me explain. There is no duality argument in the background, because the dual spaces to these Besov-type spaces, they are known, but they do not belong to the same scale. So they are quite different and they are complicated to handle. So there are many papers about characterizations of the dual spaces of Morrey spaces, which are not so easy, these characterizations. And in case of Besov spaces, where you have additional smoothness, things are getting even more complicated. But, however, if you plug in tau equals 0, then we get the same restrictions as before, in case of the classical Besov spaces. For p strictly less than 1, we did not end up with necessary and sufficient conditions. There's a very little gap. So the first case is that we look for a Morrey parameter larger than this critical quantity. Then it's the same condition as before, as in case p strictly larger than 1. If we look for small Morrey parameter, then there is a new, at the first moment, strange condition. So tau is restricted to 0, 1 over p for certain reasons. Then this means that this quantity here is between 0 and 1. So it's a weaker condition compared to the original condition for Besov spaces. So it's a weaker condition than S strictly larger than d over p minus d. But the explanation of these conditions here is quite easy. Again, we ask under which conditions these spaces are embedded into L1. And the first answer is never. But if we localize it, if we take it on a cube, then the almost if and only if conditions are these two conditions. Why almost if and only if? If we would have here a 1 in place of p, then that would be if and only if. But it's unknown whether the Besov-type spaces with S equals 1 minus tau p d over p minus d and q between p and 1, whether in this case the embedding holds true or not. By the way, this embedding result is due to Haroska and Chipchuk in 2013. It's a, in my opinion, highly non-trivial fact. So the counterexamples we have constructed that are counterexamples using characterizations of those spaces here in terms of sufficiently smooth double-sheaf wavelets. So what is my conjecture? So I did not explain up to now why we have restrictions for the validity of this characterization without an influence of the Morrey parameter on the left-hand side. At the beginning, I was almost sure there should be a dependence on the Morrey parameter of the left-hand side, and it should be weaker than this. And this is also expressed by these conditions on the necessity of these mappings, where you look for the for the meaningfulness of these scalar products. But now I'm almost convinced that these are the natural conditions up to equality here. This I don't know. I would believe that at least this range is reasonable. Why? So in the background, let me formulate it in a different way. So in 2006, Christ and Seeger have made a very interesting but rather sophisticated constructions of test functions showing that certain Triboli-Sorkin spaces cannot characterize by differences. So these constructions carry over, first of all, to Triboli-Sorkin-Morrey spaces. And then you can show that those characterizations by differences cannot take place. And this is a point where Triboli-Sorkin spaces meet these Besov-type spaces if you have p equals q. And then you can show that these spaces do not allow characterization by differences in the way you would expect. And then you need an estimate between differences and these sequence space norm of the Fourier Haar coefficients, and you are done. And it looks like that would be true. So I believe these are the natural conditions, probably except these limiting cases. What are possible applications? So as I tried to motivate before, these spaces are not made for approximation theory, they are made for PDE people. And PDE people, they do not work on RD, they work on domains. And the classical way from RD to domains is across the half space. And then a helpful tool for doing that, for switching from spaces on RD to spaces on the half space, is the fact that the characteristic function of the half space is a pointwise multiplier. And if you look for this problem under which conditions the characteristic function of a half space is a pointwise multiplier, and you transfer this question to the level of the sequence space, then it's an exercise. It's a two-lines proof to show that under the conditions of the theorem, so exactly under these conditions, the characteristic function of a half space is a pointwise multiplier for these Besov-type spaces. And pointwise multiplier means that f times this characteristic function belongs to this space whenever you start with a function from this space. So this would be one possible application I have been interested. Thank you very much for your attention. That's all what I wanted to say.
Would you like to ask any question? Okay.
Do you know anything about interpolation spaces of your interpolation properties of your Besov space?
Yeah, I know some. So interpolation is difficult, but a few things are easy. So this is the Morrey space. So I have to explain the notation. We have to take, let me take cubes. So we take I have to think about the power. One moment. It should be negative. So the notation, unfortunately, is not quite good in the sense of the notation I had introduced before. So if this condition characterizes the Morrey space, so U has to be larger than P, then one knows if you look for the real interpolation space, say here S0, then the outcome is the space, the Besov-Morrey space. Here you have S with the standard conditions. S is 1 minus theta S0, and theta is between 0 and 1. U, P, Q0, Q. So the P is fixed. Q0 here can be arbitrary. And U and tau are related as follows. This is 1 over P minus 1 over U. So this is an extension of the classical formula. If you interpolate a Besov space with LP, then you get a Besov space in between. But what concerns complex interpolation, the situation is more complicated. Then you get additional restrictions. There are papers by Lemarrier, by Savano, and also by Dachun, Yuan, and myself. So interpolation, except this formula, this is not difficult to prove, is a bit tricky. So in some sense, this is one of the properties which are not satisfactory, so these spaces do not show up on the right-hand side.
More questions? So let us thank Winfried for that.